welcome. We will continue our discussion on the topics of sampling and the Fourier transform. So let us take a look at the topics that were intended to be covered for weeks 3 and 4. We were supposed to look at sampling, which we have looked at. How do we use an impulse train for sampling? Yes, we have done that. The relationship between the impulse train and how do we translate it into into a sample domain, that also we've been looking at, and also looked at the Nyquist sampling theorem, and we also looked at some applications of that. So today there are some topics which we will be able to cover after we have covered the topic of DTFT. So we will come back to this particular section once more after we have covered the discrete time Fourier transform. However, today we will talk about an important topic called quantization. How do we go from a discrete time sequence which has got infinite precision to a sequence which has got a finite number of bits of precision? Now, this particular aspect of quantization is covered in chapter 4. After we finish chapter 4, we will go to chapter 2, section 7, where we will talk about the discrete time Fourier transform. So that is the sequence of events, though not in the same order as the textbook, but we have looked at sampling, we will go back to looking at the discrete time Fourier transform. So let us look at what are the topics that are coming up in the weeks 5 and 6. We are going to be looking primarily at the discrete time Fourier transform. It is called DTFT, and this will give us the properties. We will be studying the properties of the Fourier transform. We will be studying certain theorems about the Fourier transform and how to do the inverse Fourier transform. So basically all of these topics we are going to be looking at. The corresponding chapters in Oppenheim and Schaefer are chapter 2, section 7, section 8 and section 9. Sections 8 and 9 are basically referred to the properties of the discrete time Fourier transform. Properties and their applications. Okay, that is going to be our primary focus as we start this new chapter. Now let us take a quick recap of what we have studied in the last class and add to our understanding of what we have done in the last class in terms of the topic of sampling. So in a nutshell, when you have a band limited signal, we can then apply the Nyquist theorem to say that we can go from continuous time to discrete time without any loss of information. What is Nyquist rate? Nyquist rate must be at least as large as the sampling rate must be at least as large as 2 times the highest frequency component, and Nyquist rate is exactly equal to 2 times omega n. Now, this particular sampling process yielded for us a very important result, which said that the sampled spectrum of the sampled signal xs of j omega is 1 over Ts summation m equal to minus infinity to infinity xc. So let me take this as as a signal of interest and look at it a little bit more closely. All right. So this is the spectrum of the sampled signal. Now, what we find here are the 3 important elements which we have highlighted before, but I just want to highlight one more time. This is a scale factor, and we have many copies of the spectrum, original spectrum. So this m equal to minus infinity to infinity says that we have many copies, and these copies are shifted. So these copies are shifted by multiples of omega s, by multiples of omega s. Okay, and this is what we sketched when we looked at this particular figure where we said that the copies are centered around omega s, that is m equal to 0, at 0 which is m equal to 0, omega s which is m equal to 1, 2 omega s which is m equal to 2, and so on. We have copies on both sides. Now, we said that if you do not satisfy Nyquist condition, you will have aliasing, which is a problem situation for us. So let us go back and look at this particular case a little more closely. We will look at two copies of the spectrum, m equal to 0 and m equal to 1. So, the spectrum that we are looking at, copy of the spectrum, this is m equal to 0, and we have a copy which is at m equal to 1. Okay, so let us write down the frequency band. This is minus omega n, this is omega n, this is omega s. So, this lowest frequency will be omega s minus omega n, and the higher frequency will be omega s plus omega n. Now, if you remember, we said that Nyquist condition, that is, we do not want overlap of these spectra. So, for no overlap, we have omega s minus omega n, which is the lower frequency, must be greater than or equal to the highest frequency component of m equal to 0. So, this condition is very important for no overlap of spectra. Okay, and simplifying this, we get omega s is greater than or equal to 2 times omega n, which is the condition for no overlap of spectra. And special case is the Nyquist rate. Nyquist rate, which is omega s equal to 2 times omega n. Okay, I hope you are able to see all of these in a broad framework of saying how does the sampling work, what happens, how are the copies produced. So, these are all having a height of 1 over Ts, and they are centered around multiples of omega s, and this is what we have looked at. And let me just introduce for you that if omega s equal to 2 omega n, we call it the Nyquist rate. If omega s is greater than 2 omega n, last time we looked at this particular application, this is called the oversampled system, or the sampling process is considered oversampled if you exceed the Nyquist rate. Similarly, if you have gone below the Nyquist rate, then this is called an undersampled system. So, Nyquist sampled, oversampled, undersampled. And undersampled systems really are not of interest to us, because these are systems which have aliasing, and this is really a distortion that is very difficult. It causes a nonlinear distortion to the signal, and really it not a process that is of interest to us. So, again, undersampled signals are systems are something that we will not be looking at too much, but to know that this is what. And from here, we also looked at the aspect of how do we reconstruct the signal. So, that also we looked at. So, we said we will remove all copies of the signal. So, we will take an ideal low pass filter. Okay, the height of the low pass filter will be equal to Ts, and the cutoff frequencies on both sides, this will be minus omega s by 2, and this one will be omega s by 2. Okay, so basically this is an ideal low pass filter. We showed what the response of this system was. So, the ideal low pass filter HR of t, we showed was equal to sinc t over Ts. Okay, and we showed that how the sinc function has got sort of a ringing response, and it goes from minus infinity to infinity. It has a very unique property that it crosses. So, this is equal to 1 at t equal to 0 and equal to 0 at t equal to nTs, where n is equal to plus minus 1, plus minus 2, and so on. So, basically these are properties, and we showed how the zero crossing properties are very important in the reconstruction process. So, basically it preserves the height of the Dirac deltas at the sampling points because of the zero crossings. So, this is an important condition for the reconstruction. Okay, so this property comes into play an important property for reconstruction. Important property for reconstruction, keep that in mind because the important property for reconstruction. And we will take a quick look at that particular aspect. Remember, this is the impulse response. Basically, it has 0 crossings at Ts, 2Ts, 3Ts and so on. And when you do the reconstruction, you see that how the time gap between the Dirac deltas are completely filled by this interpolating impulse response of the interpolating filter. But in the process, you do not affect the height of the Dirac delta. Basically, you will find that all the points in between the delta functions are completely filled. So, let us look at this particular filter. Now, we have also studied discrete time systems. So, let us see if we can look at this particular system and then look at apply the process of sampling to the reconstruction filter. A very, very interesting discussion. So, let us see what we are saying. Okay, HR of t has got a Fourier transform which is given by HR of j omega. Okay, and is HR of t band limited? Is HR of t band limited? How will you determine that? You will go and look at the spectrum of HR of j omega, and in our case the spectrum of HR of j omega looks like this. It has a height of Ts and it goes from minus omega s by 2 to omega s by 2. Yes, band limited. HR of t, is it band limited? Yes. Question mark, the answer is yes. So, which means that you can apply the Nyquist sampling to the impulse response. Can apply Nyquist sampling theorem to HR of t. Okay, interesting. We can obtain. So, what we are saying is we can obtain a discrete time sequence HR of n, which is obtained from HR of t, where t is specified as some multiple of the sampling rate. Okay. Remember, we said that we will take it as t is equal to nts. However, to make it more interesting, we are going to take it at Ts by 8. Okay, just as a interesting observation for us to consider. Okay, so what do we get in this case? In this case, we get, remember, it is sin pi t by Ts divided by pi t by Ts, and we are evaluating it at t equal to n Ts by 8. Okay, this means that it's an oversampled system because Ts satisfies Nyquist rate and Ts by 8 means you are 8 times oversampled. So, this is, we are talking about an oversampled system and it is oversampled by a factor of 8. Okay. So, again just to say, okay, Nyquist theorem can be applied to any system. This is a band limited system, we are going to apply the Nyquist sampling rate. So, you can please verify that the expression that we get is going to be sin pi n by 8 divided by pi n by 8. Now, this will look like the sinc function, but it will be sampled. So, it will look like the sinc function. It will look like the sinc function on both sides. This is the continuous time function and the sampled function will be sampled at a spacing of Ts by 8. Okay, so you can just imagine what the sampled function looks like. Okay, so now that you have HR of n and you know what it looks like the sinc function, but it has been sampled at and you get the expression sin pi n by 8 divided by pi n by 8, where n goes from minus infinity to infinity. Okay. Now, from a discrete time sequence point of view, okay, remember we had studied discrete time sequences. How will you describe HR of it? HR of n is a causal or non-causal? Causal means it must start at n equal to 0 and go only in the positive direction. Now, we have HR of n is going from minus infinity to infinity. So, this is a non-causal sequence. Okay. So, what does it tell you? The reconstruction filter is a non-causal filter. Okay. We have studied it in the context of discrete time sequences, but the same principle applies even in the continuous time. So, it is a non-causal filter. Okay. And it is also a filter of infinite duration. It goes from minus infinity to infinity. Okay. Now, as a discrete time filter or a discrete time system, an impulse response of a discrete time system, now the question that I would like to ask is HR of n, okay, is this impulse response, if you think of it as a linear time invariant system, is this bibostable? Bibostable. Again, I am using this as an opportunity to reinforce some of the concepts that we have already studied. Okay. Now, how will you check if a sequence or of a LTI system is bibostable? You will say take its impulse response n equal to minus infinity to infinity, magnitude of HR of n. If the impulse response is absolutely summable and the sum is a finite number less than infinity, okay, then we will find that we will say that the discrete time system is bibostable. All right. So, now the question that we want to quickly answer is the discrete time system represented by HR of n? I want you to take this as a simple task to check for bibostability. Okay. Let us quickly do that. So, let us take the HR of n, impulse response of the reconstruction filter sampled at Ts by 8. This gives me the conditions. Okay. So, this is sine pi n by 8 by pi n by 8. Now, I want to evaluate the values. So, if you substitute n equal to 0, you will find that you get a 0 by 0 form. So, if I want to evaluate HR of 0, I will have to do the L'Hopital's rule. Okay, L'Hopital's rule says you take limit n tending to infinity, this function which is 0 by 0 form, which is sine pi n by 8 divided by pi n by 8. Okay. Differentiate numerator and denominator with respect to the variable, and then apply the same condition again. This is limit n tending to 0. Okay, this is the same as limit n tending to 0, derivative of the numerator, which is pi by 8 cos pi n by 8 cosine pi n by 8 divided by pi by 8. So, if I cancel off the pi by 8 and then apply the limit, this comes out to be equal to 1. So, HR of n equal to 0 for n equal to 0, and it is equal to 0 for other multiples also. So, if you want to write down the conditions for the checking for bibostability. So, then what we say is I want to look at the summation n equal to minus infinity to infinity modulus of HR of n. this can be written as the value at 0 it is equal to 1, I am sorry, it is equal to 1. So, I can write it as 1 plus 2 times summation n equal to 1 through infinity absolute value of sine pi n by 8 divided by pi n by 8. Okay. So, this is the value that we are going to get. Okay. Now, I am going to use the property that modulus of sine pi n by 8 is less than or equal to 1. Okay. So, this summation can be said to be less than or equal to 1 plus 2 times summation n equal to 1 through infinity absolute value of 1 over pi n by 8. Okay. And just a very quick simplification, this is less than or equal to 1 plus 2 times 8 by pi summation 1 over n. Okay, that is the expression that we have. Okay. Now, there is a result in the study of series that the summation n equal to 1 to infinity, this is called a harmonic series. So, summation n equal to 1 through infinity 1 over n, this is called a harmonic series, and this is a series that looks like it is very well behaved because as n becomes larger it becomes smaller and smaller. However, this series does not converge. Okay. Now, what is the implication of this series not converging? Then HR of n is not absolutely summable. If HR of n is not absolutely summable, this reconstruction filter is not a bibostable system. Okay. So, again we are applying some of the earlier principles to this one, but however this is a system that is which is considered weakly divergent. So, therefore, it is not a system that will create instabilities, but the basic properties you should be able to apply. Look at the impulse response, sample it, look at the discrete time signal, see if it is bounded, is it absolutely summable. All of these properties you should be able to apply to any discrete time system. So, this is what I would like. And in case you are wondering how this proof comes about, I am sure you have already studied. So, this proof comes about in the following manner: n equal to 1 through infinity 1 over n comes out to be 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5, I will just write a few terms, plus 1/6 plus 1/7 plus 1/8 and so on. Okay. Now, if you take these two terms, okay, notice that 1/4 plus 1/4 is equal to a half. Okay. But what you have is 1/3 plus 1/4. So, this summation is greater than 1/2. Okay, I hope you are seeing that 1/4 plus 1/4 is 1/2. So, 1/3 plus 1/4 greater than 1/2. Similarly, if you have 1/8 plus 1/8 plus 1/8 plus 1/8, notice that you will get 1/2. But what you have is these terms which are larger than 1/8. So, these 4 terms taken together will be greater than 1/2. So, basically what you will get is this summation is greater than 1 plus half plus half plus half plus half. It keep on adding half terms, which does not converge. Okay. So, again is the ideal low pass filter, is it a bibostable system? The answer is no. The ideal low pass filter is what you have as the reconstruction filter. It is a non-causal filter, it is infinitely long, the impulse response dies down, but it does not satisfy the conditions for bibostability. Again, It is a interesting observation I just wanted you to have, but the important thing is not the bibostability or the the convergence and all of that. The bibostability is that the reconstruction filter does an amazing job of removing the unwanted copies of the spectrum. It also does an amazing job of reproducing all the information that is missing between the Dirac deltas, and it does it without changing the value of the Dirac delta. So, the reconstruction filter, reconstruction process, I hope you are absolutely comfortable with what we have discussed. Okay. Now, we said that if you have a Nyquist sample system, the reconstruction filter must be an ideal low pass filter. Okay. Now, such a filter is not realizable in practice, so we want to have oversampled systems so that there is some separation between the copies and we can reconstruct. One way to build a practical system for converting from the discrete time to the continuous time is not to use Dirac deltas, but to use a 0th order hold or a peak hold mechanism, which will, when you look at it in the spectrum, last time we showed, gives you the purple line. Basically, it creates a distortion of the signal spectrum in a way because you have done a staircase approximation. Now, once you have done that, the ideal reconstruction filter must be compensated. So, what is the compensation of the ideal reconstruction filter? Ideal reconstruction filter is HR of t equal to sinc t by Ts. This is the 0th order hold. 0 order hold. So, this is for a practical reconstruction filter. So, the modified reconstruction filter must compensate for the 0th order hold. So, notice that this is the ideal, this is the original, this is the 0th order hold, and when you have this in the denominator, then it will compensate. Basically, wherever H0 produces a droop, this one will produce a spectrum that is going up. So, that is why you see the purple line is not, it's not just a flat spectrum. To compensate for the purple line that is drooping, you will find that the low pass filter now will have a slightly boosted at the edge frequencies. So, this is what a practical reconstruction filter looks like. So, hopefully now you have a very good understanding of the process of sampling, the process of reconstruction, how to do practical reconstruction, when do you do oversample, why do you do oversample, all of those things are hopefully are all together.